Thank you. Thank you. First of all, I want to thank Helmut for inviting me to this program, which I think will be excellent and useful for everybody. So, because I have such a broad scope, I will start from the beginning, from the definition of a fluid. So consider, say, a bounded domain M in Rn, and consider the motion of ideal incompressible fluid. So what is an incompressible fluid? Fluid consists of fluid particles. So we have continuum of fluid particles. If the particle at some moment was at some point, then after some time it moved to some other point. So the motion of fluid can be regarded as permutations of fluid particles depending on time. And we can consider different classes of such permutations. In the classical fluid mechanics, we consider permutations which are produced by smooth diffeomorphism of our domain, which preserves the volume element. So consider D is the set of Xi M to M, so diffeomorphism, such that dxx dx identically 1. The regularity of this diffeomorphism usually is not very material, should be high enough, but if it is important, we can write here some accents which regularity is this diffeomorphism. And Xi is an element of this group, is a diffeomorphism which can be regarded as a position of configuration of a fluid. No, in fact, it is all related to some initial configuration, but all configurations are here at the same level. So in fact, we have to consider D not as a group, but as a homogeneous space, because the exact initial position of the particles is immaterial. But with some liberty, we take it as a group. Now, fluid flow is Xi depending on T. Just time-dependent fluid configuration as usual. Now, to define the dynamics, the most convenient way is the following. We can embed this group D into space L2 from M to Rn, because any map of domain into itself is at the same time the map of this domain into ambient space. This is a physical space. Here is a natural kinetic energy, namely the square of L2 norm. So kinetic energy equals 1/2 of what? No, equals. So if we have Xi of T is position depending on T, Ct dot velocity. So if we take T dot of x, so this velocity is associated with a fluid particle. Yes, so it is not velocity field, but simply velocity vector function. So it is integral over m 1/2 ct dot of x square dx. This is kinetic energy. Now the motion of the fluid is defined by the general Hamiltonian principle. Consider the flow Ct, t between 0 and some t capital. And suppose we have known xc0 and xc t capital fixed. They are given. Then if we have a trajectory going from xc0 to xt, then this trajectory satisfies the following. We have to write j, the action, integral from 0 to t, integral over m 1/2 ct dot of x square dx dt. And then it should be a stationary point for this action functional among all the trajectories such that ct in d. So this is the general principle of mechanics, and it was used to derive the equation of fluid, I think first by Lagrange himself. Now to derive it, I will use the following fact, which is also from the general mechanics. So if we have some Euclidean space, finite or infinite dimensional, and we have a manifold in this, say this manifold D, and it is embedded into Hilbert space. Yes? And we have a motion along this D, Ct, such that this is geodesic. Then we know that Ct double dot acceleration is orthogonal to T d at the point Ct. That acceleration vector in the whole space is orthogonal to this manifold. Yeah? Now it can be formally derived from this Hamiltonian principle. Now, how does it look in our case? So, what is the tangent space to our manifold D, and what is the normal space? So Td at the point Xc is the set of vector fields, say V of x, such that if we say V small of y is V of Xc minus 1 of y, and then divergence V small of y is identically 0, and V small on the boundary of our domain is parallel to the boundary. So this is the description of the tangent space, which can be easily derived from the definition of D itself. Now, this vector field V is divergence-free and tangent to the boundary. Now, if we consider the orthogonal complement in L2, then it is known that T C D is the set of W of X such that is W of Y is then W of Y is gradient of some function phi of Y. So the orthogonal complement in L2 to the incompressible vector field consists of gradient vector fields. Yeah? No, it is Weil, Hodge, and up to Kirchhoff decomposition. So this means that this equation, which is written here, Ct dot double dot acceleration is orthogonal to the tangent space. So it belongs to the orthogonal complement to the tangent space. And this means that Ct double dot of X equals gradient phi at the point Ct of X for some function phi. No, in the fluid dynamics, it is customary to use notation phi equals minus p, and p is the pressure. Yeah? So if you wish, this is definition of the pressure in the fluid dynamics. Because interestingly, that the pressure was found, no, the notion of the pressure was introduced, I think, by Pascal in the modern meaning, but he found it experimentally, different properties of the pressure. And now we can derive all the properties of the pressure from these general definitions. So, yes?
You want phi to depend on t as well.
Phi depend on what?
On t?
Of course. Yes. Yes. So let me write minus gradient phi. Yes. Now, so this is the equation which is called Lagrange equation, and it should be supplemented by next equation, that Ct in D. This means that C is a map from M to M, a diffeomorphism, so it maps the boundary, if it exists, also into the boundary, and preserves the volume element. Now, the other form of the fluid equation is the Euler equation. So let me do it. So here we have second order equation for the fluid position, Lagrange equation. And the Euler equation is the first order equation for the velocity field. So let us write u of xt is Ct dot Ct minus 1 of x. So if we have the fluid flow, then u is a velocity of a particle which at given moment t is at given point x. So we have to distinguish between the fluid particles and the points of our flow domain. So this is a velocity field, and it satisfies divergence u respect to x is 0, and on the boundary normal velocity is 0. So this is a new variable, which is called the Eulerian velocity field. It is not a dot. And we have to rewrite this equation in terms of the Eulerian field. Note to this end, we have to express ct, the acceleration, in terms of velocity. And the result is the following famous equation, du dt plus gradient u times u plus gradient p equals 0. With this 0, un on the boundary is 0. So these are the Eulerian equations, and both Lagrangian and Eulerian equations are useful in the study of fluid. I think they are equally useful, but now I want to derive even more useful equation, which may be called vorticity equation. Okay. So consider again our D. D is embedded Riemannian manifold. And now consider some eta fixed element of D. And consider the following transformation. Xi transformed to Xi times eta. Composition with eta. It is called the equals r eta Xi. So this transformation is a right shift. And we can see from the definition that right shift to D is isometry. Because if we move to the right, then if we take the tangent vector and then produce this right shift, it will transform it to another tangent vector. And the energy or its norm in this Riemannian metric, which we defined, embedded Riemannian metric, will not change because the corresponding integral will be obtained by just the change of variables in the same integral where Jacobian is 1. So this is an isometry. So we have a group, large group of isometries. So our metric on D is right invariant. Then we can produce a lot of integrals of motion using the Noether theorem. So what is Noether theorem? Suppose we have a Riemannian manifold D, and suppose we have a one-parametric group of isometries of these. So say f to d to d is one parametric group of isometries. And suppose that X is a vector field which is generator. of this group. Then just a minute, if CT is a geodesic on D, if, then the scalar product CT dot x at the point CT is constant. So this is the general form of the Noether theorem. For example, if we have the motion on the surface of revolution, then the angular momentum is constant because just a minute. Yes, it is constant, of course. So in this case, I don't find enough chalk.
It's nothing in this.
Okay. Oh, also not much, but in our case, suppose we have this one parametric group of right shifts. So we have to this right eta tau. So d tau eta tau of x is some w of eta tau of x. Yes, this and eta 0 of x is x. So we have to fix velocity field w, and these equations describe us one parameter group of transformation, and we consider r eta tau d to d. And now consider the field x of xi at the point xi. Xi is d tau r eta tau of xi at tau equals 0, as usual. So this is the generator, the vector field, tangent vector field, which is a generator of one parameter group of right shifts, and we know that right shifts are isometries. And then how to describe x of xi if we know if w is given. So x of xi at the point x equals xi star w at the point x. So the vector w at the point x is transferred to the point xi of x and multiplied by the Jacobian matrix. So it is written this word. And so our Noether theorem says that this scalar product x of ct dot is 0. No, so this means that integral ct star of w of x times ct dot of x dx is constant. I'm sorry, it is constant. Integral over our domain M. So this velocity, this field, no, not velocity, but field W here, the lines of this field, is transported by the flow. It is distorted by the flow, and this integral remains constant. Now, in particular, we can take
So where's the star? Down.
excuse me?
The star is down. Let's push forward.
Star is down. Now, in particular, let us take the W is a field which is concentrated on some line gamma. So it is delta-like vector field, which is proportional to a tangent field on gamma, multiplied by delta function in transversal direction. Then we have the following. If that integral over ct of gamma u times ds is constant, where u of xt is ct dot ct minus 1 of x. It is the Eulerian field. So here we have such interesting interaction between Eulerian and Lagrangian pictures. So if the contour of integration is moved by Lagrangian flow, just physical fluid, and we consider the Eulerian field, then the circulation, this means integral of the velocity field, Eulerian velocity field, along this changing in time contour is constant. Yeah? Now, if we use the Stokes theorem, this means that vorticity u at the time t equals now here we have two equivalent ways. So what is vorticity? If we are in three-dimensional space, then vorticity can be regarded either as a two-form or as a vector field. Yes. So mechanics. In mechanics, we prefer vector field. So it is just ct star curl u. Let's put dot 0. So vorticity, the vector field of vorticity, is transformed by the flow as a vector field.
Question. Yeah. Can you repeat how did you choose your W there? So you
What?
wanted to be supported along the curve?
No, we can imagine here a thin tube, so that the field W is 0 outside this tube, and the flux through this tube is, say, 1. Yes? And then the tube is shrinking to just a line. And the limit will be, no, it can be called distributional field, or it can be a current. So this singular limit. But if we push to the limit, we'll have this.
And you also want W to have zero divergence, right?
Yes, this also has zero divergence, and definitely is tangent to the boundary. Yeah, so this is the basic equation, which we can call the vorticity equation. So why it is so important? No, first of all, we can associate with this this field curl U a lot of different invariants. So we have a bunch of integrals, especially in 2 dimensions, which I will go in a minute. And now let me formulate a theorem which will make significance of this equation even better. So theorem. So given the field, let's say omega is such that curl omega divergence omega is 0 in M. Suppose M is, say, simply connected. To avoid some unnecessary problems. There exists unique vector field U of x in M such that curl U is omega, divergence U is 0, Un on the boundary is 0. Yeah, so we can restore the velocity field from the vorticity field. And this U, let us denote by curl minus 1 of omega. And so the equation of motion, which is equivalent to the Euler and to Lagrangian equation, can be written as follows. Ct dot, just time derivative, equals curl minus 1 omega 0 at the Ct minus 1, the point C. T. Now, here I tried to be meticulous where each vector is applied. So I have to add here this to indicate where we take apply it instead of writing down nested brackets. So this means the following. What is omega 0? Omega 0 is curl xi0 dot. So xi0 itself is identity, say. So we start our fluid flow from the position which we take a reference position. So the corresponding element of group of diffeomorphism is identity. Now, given initial velocity, xi dot 0, at the moment 0, we find its vorticity, omega 0. And then at every other moment, if we have xt, we transform vorticity, initial vorticity omega 0 with this transformation xt. I'm sorry. Xi. It is transform. Or it is the same as we write, I'm sorry. Xi t star omega 0. Of course, this. So we transform initial vorticity with this diffeomorphism xi t and take inverse vorticity, and this will be velocity field, which is time derivative of diffeomorphism xi. Yeah. So this equation is the vorticity equation. And it is really the most useful in the study of the fluid behavior. Yeah. Now, let me see. Okay. The next is how to specify it if we have two-dimensional fluid flow. This was related to three-dimensional flow. In two-dimensional, we know that vorticity has just one component. So we have x, y, and z. Vorticity, if the flow is in the xy plane, then vorticity is directed in z. So vorticity omega is a scalar function, is du2 dx1 du1 dx2. So it's just a scalar function. And vorticity is transported by the flow as a scalar function. Just a minute. N equal 2. So omega of xt equals omega ct minus 1 of x 0. So we have to find the point where this particle, which is now at the point t, x was in the beginning, and take vorticity at this initial vorticity at this point. And then we write the following thing. In two-dimensional case, very useful thing to represent incompressible flows tangent to the boundary is the notion of stream function. Which I think is a primitive form of the generating function in symplectic geometry. This means that if divergence u is 0 and un on the boundary is 0, is the same that we write u1 is dψ dx2, u2 is minus dψ dx1 for some function psi, and such that psi on the boundary is constant or 0. Yeah? So we can define the stream function and describe everything with stream function, which is always better than to use the vector fields. So now in the last 15 minutes, I want to introduce some problems here.
Is that higher dimension something related to this? Or?
What?
But this is very specific.
It is specific to 2 dimensions. No, by the way, in 2 dimensions, group D is the same as group symplectomorphisms. Yes, so or Hamiltonian symplectomorphism. So I think the main intersection with symplectic geometry is n equal 2. Yeah. No, we can consider similar equations as equations of geodesics on the group of symplectomorphism in any dimension with L2 norm. So I think Boris Hessin will tell us about it when he will come, because there is a striking similarity with 2-dimensional case and very good results. Yes, and to say what is the consequence of this? The consequence of this is the following. So we have a bunch of integrals, so vorticity integrals. We can take any function, say f of s, any function, no, reasonable function, and consider integral over m f of omega dx, any function of vorticity. And because vorticity is transformed by transformation preserving the volume element or area element, this means that it is a constant. So no, in particular, the maximum and minimum of vorticity is constant. Any moment of vorticity is constant. So we have a lot of integrals which helps in many problems. Now, historically, the first equation which was studied and where the first real results were obtained was just this vorticity equation, which was written there. So because what I told up to now was pure formalism, we did not talk about existence, uniqueness, and functional classes, and so on. So we can introduce now the following notion. Say DHS is the set of Xi in D, and at the same time Xi in, say, Sobolev class HS. So these are diffeomorphisms or Sobolev. Or similarly, DCK alpha, set of Xi is D, such that Xi in CK alpha. This is the class where the more classical functional space. Or we can write here any reasonable functional space. And every time we ask whether there exists a unique solution of equation. No, so we consider this vorticity equation. So we have to write omega at the time 0 belongs to, say, DHS. Omega is a result of differentiation DHS minus 1. Yes, or to this class or some other class. And then ask whether there exists a unique solution. So the first fundamental result was obtained by Liechtenstein and Nikolai Günther around 1925. So it's really old results, but it requires development of a lot of estimates which were used in all the theory of partial differential equation. Is the following. Suppose omega 0 in H in C, it was K alpha, where K is more or equal than 1. It's enough. Then we are, I'm sorry, without the D relates to diffeomorphisms. Then there exists unique solution Xi T in D C, no, if it's K, so K plus 1 alpha, so omega is less regular than diffeomorphism for module T less than some C. C depends on omega 0, omega of 0. So this is a local theorem, local existence uniqueness theorem for this Vorticity equation. No, because Vorticity equation is equivalent to the Euler equation and to the Lagrange equation, so this works for all of them. Now, the method of the proof of this theorem was quite remarkable and I would say unique in all of mathematics. So consider this equation, Vorticity equation.
So this is true in all dimensions?
In all dimensions, from 2 to infinity. No, they wrote up in 3 dimensions, but it was clear that it's good in any dimension. So the proof is, so consider the equation, so proof. No, like this. Consider the equation d xi dt equals, say, f of xi, where xi is d c k plus 1 alpha, and f is the right-hand side of that equation. Equals curl minus 1 ct star omega 0 times ct. That's it. So f of xi is a vector field on the this group f of xi t d c k plus 1.
You want that without the t, so
Excuse me?
f of t is called, no, you don't want the t, so this second line from below. F of t is equals curl inverse of psi, which
Yes.
and the last t.
Yes.
One more.
Yes, and one on. Yes. So we have this is a vector field. No, at least for now, formally vector field. But what they managed to prove? Remarkable fact. C is a smooth, even analytic vector field on D, Ck plus 1 alpha. If you studied anything related to partial differential equations, you would see that this situation is quite unique. Because if we consider any evolutionary equation, like wave equation or heat equation, something like this, then the right-hand side is an operator which is not everywhere defined, is only densely defined, is everywhere discontinuous, is unbounded, even locally. So it cannot be regarded as an ordinary differential equation in our sense. Or we can do it formally, but the results or the theory of ordinary differential equation will not apply there. So therefore, we require quite different methods. Here, what is written here, that equation on above, is an ordinary differential equation on a Banach manifold in a direct sense. Yes, so all the definitions which are written in the textbook on ordinary differential equations are applied here. So we can directly apply the standard local existence uniqueness theorem, which is proved by, say, the Picard iterations, and have our result without any effort. Moreover, this analytic part was proved by Liechtenstein, but he did not make conclusions from it. Yes, conclusion is that by another standard theorem, solution is also analytic in time. Yes, so this means that, okay, I think I can write here. This means that Ct is dck plus 1 alpha. So it is an element, so it consists of diffeomorphisms, which are not C infinity. They have some, no, maybe weak and small, but singularities. But Ct is C omega, so analytic curve from, say, minus t to dc k plus 1 alpha. So it is analytical curve in the space of diffeomorphism. It's possible. In particular, Ct of x, it is a curve minus tt to our domain in a finite dimensional domain, is analytical curve. So the trajectories of the particles are analytical curve. Yeah. No. To have the final stroke of this story, consider the stationary solution. Of Euler equation. This time it will be Euler equation. So it will be some flow which satisfies the equation nabla u times u plus nabla p is 0 without du dt. Yes? we have plenty of such solutions. We have infinite dimensional family of such solutions. So these solutions can be of moderate regularity. Yeah? So they may have some small singularities. But the flow lines are analytic. Yes? So if we consider corresponding stream function, psi is constant, is analytic. While psi is only c k plus 1 alpha. Yes, so we have a function. No, it is a strange class of functions which did not appear in analysis or appear very rarely, which here are relevant. Okay, it led to some dramatic story in Paris when I was invited to be in a examiner for some doctoral thesis. Yes, and the defendant proved that for some boundary regularity, limit regularity, which was achievable by that time, the trajectories of particles are C infinity. Yes, and he referred to some other previous thesis where it was proved that for higher regularity, like here, they are analytic. So I asked him, but I think that it was established by Liechtenstein in 1925. So we all rushed to the library, found the paper of Liechtenstein, and it turned out that he really was in a position to establish this result, but he did not. He proved that the field is analytic, yes, by a very ingenious way. How did he prove it? But he did not make this conclusion because he did many other things. You know, simply one person cannot do everything. Yeah? And now we have to appreciate that in 1925 there was no notion of Banach space at all. This term appeared 10 years after that. Now the notion of ordinary equation in Banach space, which is the same as equation in Euclidean space, became more or less accepted only in 1960s. And next, that the complex analytic structures in Banach manifolds, I think they are still an open space. So what he did, he had to produce from the scratch all computations and estimates for the Picard approximations, which took maybe about 100 pages, instead of referring to a standard theorem. Okay, so I think my time is over, and I did not mention the problem. So if you give me one more minute, I will mention just two problems. So one problem is that the theorem which was proved is local in time. So the question is, what happens when time is growing? Does the theorem hold? Now, in two-dimensional case, it was proved in about 1933 by Volibner, and then it was improved further, that solution exists for all times, using these vorticity integrals which I have produced here. It is in two dimensions. In three-dimensional case, it is an open problem which costs $1 million. Now, yes, but there exists opinion that if you wish to have $1 million, there are simpler ways to get it. Yes, so there is one problem, and the other problem is appears to be more accessible and not less interesting, is what happens in 2D. In 2D, we know that solution exists for infinite time, but we can ask all other questions. So how does it look when t goes to infinity? What is the time asymptotic or long time behavior? Yes? No, as an answer of a possible result here, I can tell you that now there exists strong evidence that in the space of velocity fields for the Euler equations, there exists a real attractor, in spite of the fact that this is a conservative, even Hamiltonian system. It has space to hold a real attractor, so all solutions converge to some much smaller set. But I have no time. It will require another several lectures to approach it. So thank you for your attention.
Thank you very much. Very interesting lecture, and I'm sure we'll find the opportunity to listen to more of the things.